So today we're talking about problem number 7 for continuous charge distribution. And here we have a non-conducting ring of radius r. The ring is charged with a positive charge and it is just uniformly distributed on the ring. So the first step of this problem is to, in order to find the x component, I always want you to start with taking symmetric positions on your charged ring, and we can choose any arbitrary position on x and call that a constant, and we're going to identify what direction the electric field would be to two symmetric positions. So if I take the top position and I know that positive charges, or a piece of the positive charge at the top, is going to have an electric field out, at this position on the x-axis, it'll go down and out. So this is my electric field. For this piece of charge at the bottom of the ring, it'll come up and to the right, which lets us know that the y component of our electric field is going to cancel out. And you can do the same thing for these positions and see that both the y and the x components end up having an electric field equal to 0. So all we really have left is electric field pointing in the positive x direction. So now we have to do the steps to calculate that electric field, and for these types of problems you always want to start with the fundamental principle, even though I know you can plug in components and all that other stuff in advance. So this earns you points on an AP exam, just taking the equation in your equation sheet and writing it down to start. Now, the next thing we have to do is we need to figure out how do we get just the x component, because that's really what I'm looking for. The angle that will help us get that is this angle right here along the x-axis and the radius. So this is our r squared in our equation, the distance from our piece of charge to our position. And that translates here as well as here because they're alternate interior angles. So these are all theta. The next thing we need to recognize, so let me write it out, that the x component is cosine theta. The next thing we need to substitute in our equation is the equation for r. So because it's a hypotenuse in a right triangle, I know that I've got a constant radius of a circle, which is not little r, but big R. And I've also got a distance here that I myself have defined to be x. I know that my distance is going to be big R squared plus x squared. And then from there, we can plug in all the parts of our equation. This is going to be the square root of r squared plus x squared, all quantity squared. And I know I can cancel the square root with the squared, but I'm not going to do that because of this cosine theta. Now, unfortunately, we've got a q here and a theta here, which are both changing, and we need to write our integral so that we don't have any, we only have one variable that we can integrate. The r and the x are both constants, so essentially in the end I want to pull out all those constants, but you always want to rewrite your equation so that there's only one varying variable and everything else is constant, and then you can integrate with respect to that variable. So this is a trick I want you to know how to use in multiple continuous charge distribution problems, and it's the fact that even though I'm looking for cosine of this electric field, because the angle here and the angle here are the same, I can use similar triangles to find cosine of theta using this triangle, similar triangle right here. So the cosine theta of that is going to be x over r, and, oh sorry, wrong r, x over little r, which then would translate into x over the square root of big R squared plus x squared. And then I'm going to plug that into my equation and things can start simplifying out. I've got dq over the square root of r squared plus x squared times x over the square root of r squared plus x squared. And then I know that I can pull out all of my constants here. I also forgot to square this denominator. And since all of these are constant, I'm going to write my equation as kx all over the r squared plus x squared to the 3/2. Why? Because the square root is is 1/2 for your power, and then obviously I have 2 of them here and then 1 on the right, so 3/2. And then that gets rid of our cosine. I still have a dq, which is my only variable, and I can integrate with respect to that variable, which is really q to the 0 because it's just 1. And then I need to think about my limits. Well, it tells us that the full charge is big Q, so I'm going to go from 0 to big Q, and that'll just give me EXK is equal to KX big Q all over R squared plus X squared to the 3/2. And obviously you would subtract it by plugging in, subtract the 0 when you plug it in, but that just cancels out. So here is your final answer. This is one of the easiest derivations that we have to do for continuous charge, as long as you can remember this concept and then carry that over into some of the others as well.